The cosmos is vast beyond imagination. Billions of stars, even more planets. And all of it existed long before our appearance, for billions of years. Extraterrestrial life could have arisen, evolved, and vanished long before humanity ever emerged. And not just once, but countless times. Imagine if this were ordinary for us. Archaeologists would regularly discover artifacts that belonged to no known civilization on Earth. Neil Armstrong might never have reached the moon if a lunar defense system had mistaken Apollo 11 for a UFO and shot it down halfway there. Between Earth and Mars, gigantic engineering structures of unknown origin would drift through space, occasionally ejecting debris into the vacuum and polluting vast regions around them. One could even imagine an interstellar highway, a high-speed route used by alien spacecraft traveling between star systems, a route that runs straight through our solar system, simply because their lawyers didn't think it necessary to ask permission from the inhabitants of a small blue planet. And to compensate for the inconvenience, once a year they might drop off elementary school textbooks, an awkward but sincere sorry. But as far as we know, nothing like this is happening. We tend to think that humanity might be the only intelligent civilization in the universe. The reason is simple. We have no evidence for the existence of extraterrestrial intelligence. As Carl Sagan liked to say, absence of evidence is not evidence of absence. Yet one man once asked a question that turned this issue into one of the most intriguing scientific mysteries of modern times. In the summer of 1950, in the cafeteria of Los Alamos National Laboratory, theoretical physicist Enrico Fermi was having an informal lunchtime conversation with three of his colleagues. They were discussing cartoons from The New Yorker in which UFOs were depicted stealing trash cans from the streets of New York. The conversation began in a joking tone, but gradually shifted to a more serious topic. They began discussing recent reports of unidentified flying objects that had flooded the press after the famous Kenneth Arnold UFO sighting incident. Suddenly, Fermi asked a simple question, one that would permanently change our understanding of humanity's place in the universe. Where is everybody? No explanation was necessary. His colleagues immediately understood that he was referring to extraterrestrial civilizations. This brief question later became known as the Fermi Paradox. Fermi's colleagues, Emil Konopinski, Herbert York, and Edward Teller, later recalled that the question caught them off guard. Fermi even performed quick calculations on a napkin, showing that under reasonable assumptions about interstellar travel speeds, the entire galaxy could be colonized within a few million years. A mere instant on cosmic timescales. Where is everybody? The question sounds simple, but behind it lies a profound scientific problem that has troubled astronomers, philosophers, and futurists for more than 70 years. 10 years later, astronomer Frank Drake attempted to approach this problem mathematically. In 1961, he proposed a formula that intensified interest in the search for extraterrestrial life and provided a scientific framework for discussing extraterrestrial intelligence. The Drake equation attempts to estimate the number of civilizations in our galaxy with which communication might be possible. The equation describes the probabilistic chain leading to the emergence of communicative technological societies. Importantly, the purpose of the equation was not to produce an exact number. Instead, it was meant to break the problem into a series of scientific questions that could be studied individually. As Drake later admitted, the formula was intended more as an agenda for research than as a precise predictive tool. Let us substitute values often discussed in modern astronomy. Calculation. N equals 10 times 1.0 times 0.4 times 1.0.1 times 0.1 times 10,000 equals 40. According to this calculation, there could currently be 40 civilizations in our galaxy capable of communication, which immediately raises another question. Why haven't we seen any of them? The night sky appears boundless to us, yet when we look up, we are actually seeing only a tiny fraction of the cosmos. On the clearest night, a human can see at most about 2,500 stars with the naked eye. Almost all of them lie within 1,000 light-years of Earth, roughly 1% of the diameter of the Milky Way galaxy. This is like looking through a keyhole in the front door of a 100-story building and assuming that what you see through that narrow opening represents the whole structure. In the observable universe, there are estimated to be between 10 sextillion and 1 septillion stars. In simpler terms, for every grain of sand on all the beaches of Earth, there are roughly 10,000 stars somewhere in the universe. Between 5% and 20% of those stars are similar to our Sun. Even using the most conservative estimate, that gives us around 500 quintillion Sun-like stars. Now imagine that 1 out of 5 of those stars has a planet similar to Earth, a world with liquid water and conditions suitable for life. That would amount to roughly 100 billion Earth-like planets. In other words, for every grain of sand on Earth, there could be 100 potentially habitable planets somewhere in the cosmos. Think about that the next time you find yourself standing on a beach. Now, let us take an extremely conservative assumption. Suppose that over billions of years, life appeared on only 1% of those planets, and that only 1% of those life-bearing worlds developed intelligent civilizations like ours. Even with these modest assumptions, the result would be around 10 quadrillion intelligent civilizations across the universe. That would imply that within our own galaxy, the Milky Way, there might be 1 billion Earth-like planets and perhaps 100,000 intelligent civilizations. But there is another side to the argument. For us to detect evidence of another intelligent civilization, it is not necessary for thousands of them to exist within our galaxy. Just one long-lived civilization would be enough. If even a single civilization survives for thousands or millions of years, then the galaxy should not appear empty. All it would take is one very long-lived and technologically active civilization to leave traces everywhere. Consider the scale of cosmic time. The Milky Way is about 13.6 billion years old. Earth is roughly 4.5 billion years old. Modern humans have existed for only about 300,000 years, and our industrial civilization has existed for barely 200 years. If another civilization had appeared just 1% earlier than we did, on a cosmic timescale, it would be 100 million years ahead of us. What could be achieved in 100 million years? One might build ring worlds around stars. One might move entire stars from one place to another. One might send billions of probes into every corner of the galaxy. Imagine a civilization that has mastered interstellar travel. Perhaps it has built something like a galactic transportation network. It does not even require faster-than-light travel. Even slow expansion would be enough. Suppose their spacecraft travel at just 1% of the speed of light, about 3,000 kilometers per second. For us, this is unimaginably fast, but according to physics, it is entirely plausible. Distances between neighboring stars are only a few light years. Such journeys might take hundreds of years. Is that long? For an individual human, yes. For a civilization that exists for millions of years, not at all. Colonists would first settle the inner planets and moons of their own system. As their colonies expand, they would require more resources and more space. Eventually, they would be forced to travel further, leaving their home system. They might build generation ships, enormous vessels carrying entire populations across the void. Or they might send robotic probes first, machines designed to explore star systems, mine resources, and prepare new worlds for habitation. If a planet is unsuitable for life, they might attempt terraforming, altering the atmosphere and climate of an exoplanet to make it habitable. Even if thousands of years pass between expeditions, the galaxy could still be colonized in just a few million years. This would not resemble a traditional exploration campaign. It would resemble biological reproduction, a self-propagating wave spreading through space. Some estimates suggest that the entire galaxy could be filled with colonies within hundreds of thousands to tens of millions of years. Now imagine that such a civilization emerged just 1 million years ago. On cosmic timescales, that is practically yesterday. For comparison, the first members of the genus Homo appeared on Earth roughly 2 million years ago. Yet even within a single million years, a wave of interstellar colonization could have spread across a vast region of the galaxy. Which means that if even one civilization ever began such an expansion, we should already be living inside a galaxy that has long since been colonized. And remember, our galaxy is 13 billion years old. Such enormous interventions in the structure of a galaxy should leave traces. Even if the civilization itself went extinct long ago, its artifacts might remain. Space is an excellent preservative. Possible traces might include dead probes, autonomous machines capable of functioning for millions of years, radio noise, signals that continue traveling through space long after their creators vanish, thermal signatures, according to the laws of thermodynamics. Any technological activity produces waste heat. Even if a civilization deliberately tried to remain hidden, its entropic footprint should still be visible. We should observe anomalies in stellar motion, unexplained bursts of energy, or strange artificial objects in orbit around stars. But we see nothing, no signs of expansion, no signals, no ancient machines, only silence. And this is the moment when the question asked by Enrico Fermi becomes truly unsettling. Where is everybody? We hear nothing, absolutely nothing. No signals, no traces, no hints. Complete silence. Our sun is a relatively young star by cosmic standards, yet the universe contains stars that are far older. Around some of them may orbit planets similar to Earth, only billions of years older. It is logical to assume that if life emerged on such worlds, their civilizations might have advanced far beyond our own. To illustrate this, compare Earth, about 4.54 billion years old, with a hypothetical planet X that is 8 billion years old. This roughly corresponds to the average age of planets orbiting red dwarf stars, which are the most common stars in the universe. If life on such a planet evolved in a way even roughly similar to life on Earth, imagine the advantage provided by an additional 3.5 billion years of evolution. A civilization only 1,000 years ahead of us would already appear almost magical. A gap of 1 million years would be even more dramatic. Their technologies would likely be as incomprehensible to us as human civilization is to a chimpanzee. And that is only a difference of 1 million years. To describe the technological level of civilizations, scientists use a well-known concept known as the Kardashev Scale, proposed in 1964 by Soviet astrophysicist Nikolai Kardashev. This scale classifies civilizations according to the amount of energy they are able to harness. A Type 1 civilization is capable of utilizing nearly all the energy available on its home planet. Humanity is gradually approaching this level. By some estimates, we are currently around 0.73 on the Kardashev scale. A Type 2 civilization can harness the energy of its star. The classic example is the hypothetical Dyson sphere, a megastructure completely surrounding a star and capturing most or all of its energy output. For us today, even imagining such technology is difficult. A Type 3 civilization would control energy on the scale of an entire galaxy, perhaps even something like the Milky Way itself. This may sound like science fiction, but let us return to our hypothetical planet X with its billions of years of additional development. If a civilization similar to ours had emerged there, it might well have reached Type 3 by now. Such a civilization would likely find interstellar travel and galactic colonization entirely feasible. Imagine autonomous machines traveling to distant star systems, using local resources to construct copies of themselves, and then sending those copies further into space. These machines are often called von Neumann probes, named after mathematician John von Neumann, who first described the concept of self-replicating automata. Even without faster-than-light travel, such a process could theoretically lead to the colonization of the entire galaxy in roughly 3.75 million years. On cosmic timescales, that is almost instantaneous. If this still sounds too abstract, consider the results of computer simulations. Astronomers from the University of Rochester once simulated the possible colonization of the Milky Way. In their model, spacecraft traveled extremely slowly, about 10 kilometers per s. The maximum distance between colonized systems was 10 light years. Each journey took about 300,000 years. Every colony launched a new expedition roughly every 100,000 years. These time spans are enormous, far longer than the entire history of human civilization. Yet even under such slow conditions, the simulation showed that a technological civilization could spread across a large portion of the galaxy within about 1 billion years. If even 1% of intelligent civilizations eventually reached Type 3, then our galaxy alone should contain thousands of such super-advanced societies, and their activities should be visible. But we see none. Why? Perhaps we misunderstand how the universe works. Perhaps advanced civilizations deliberately hide their presence. Or perhaps we truly are alone in the Milky Way, or simply appeared too early. Let us examine some of the most widely discussed explanations for the Fermi Paradox. One possible answer to the Fermi Paradox is that we might be an extremely rare phenomenon. This idea is known as the rare earth hypothesis. It was proposed by paleontologist Peter Ward and astronomer Donald E. Brownlee in their book, Rare Earth: Why Complex Life is Uncommon in the Universe. According to this hypothesis, complex life may arise extremely rarely because it requires an extraordinary combination of conditions. Possible requirements for complex life. 1. Galactic location. Within a relatively safe region of the galaxy, far from the intense radiation and frequent supernovae near the galactic center. 2. A suitable star, stable, with the right mass and long lifespan like our Sun. 3. A large moon. Earth's moon stabilizes our planet's axial tilt and climate. 4. Gas giants. Jupiter may shield inner planets from frequent asteroid bombardment. 5. Plate tectonics, necessary for recycling elements and stabilizing climate. 6. A magnetic field protects the atmosphere from stellar radiation. 7. Proper chemical composition. Sufficient water, carbon, oxygen, and other essential elements. If even one of these factors is missing, complex life might never appear. In that case, Earth could represent an extraordinarily rare coincidence of conditions, despite the immense size of the universe. But science also allows the possibility that life elsewhere might be radically different from us. Let us move beyond carbon chauvinism and consider other possibilities: silicon-based organisms, methane-based ecosystems, plasma-like structures, or synthetic life forms. Such beings might live under extreme gravity or on extremely hot planets. Imagine a life form based on silicon rather than carbon. Such a creature might thrive at temperatures that would instantly destroy terrestrial life. A living stone. Its existence would be radically different from ours. If you are literally a piece of rock, you do not need a roof over your head. You do not build houses or cities. You might have no eyes or ears at all. Your entire solid body might function as both receiver and transmitter of radio signals. Such a civilization would not need antennas. Even if it achieved interstellar travel, it might never build megastructures like Dyson spheres. Its star might not even be its primary energy source. Perhaps its planet has no star at all. The technological path of such beings would be completely different. Different technologies, different modes of thought, different methods of communication. And that may be why we fail to detect them. We are searching for something that might truly exist. There is another, more disturbing hypothesis. It was proposed in 1996 by economist and futurist Robin Hanson in an attempt to explain the Fermi Paradox. According to this idea, somewhere along the path from simple chemistry to a spacefaring civilization, there exists one or several extremely difficult evolutionary barriers. Most civilizations fail to overcome them and disappear. This hypothetical barrier is known as the Great Filter. It may lie behind us or ahead of us. Position of the filter, what it means, consequences for humanity. Behind us, we have already passed the most difficult stage. Good news, we likely have a long future. Ahead of us, the most dangerous stage is still to come. Bad news, we may not survive it. Possible filters behind us. The emergence of life from non-living matter, abiogenesis. The appearance of eukaryotic cells. The development of multicellular organisms. The emergence of intelligence. Possible filters ahead of us. Nuclear war. Artificial intelligence escaping human control. Engineered pandemics. Ecological collapse. Nanotechnological disasters. Under this hypothesis, most intelligent life in the universe has already been eliminated by the Great Filter. If the filter lies in the future, it means humanity may be approaching the most dangerous stage of its development. There are many possible ways a technological civilization might destroy itself. Global war, uncontrolled AI, engineered pathogens, climate catastrophe. This hypothesis forces us to confront an uncomfortable thought. Our civilization may be far more fragile than we like to believe. The silence of the universe might not indicate emptiness. It might indicate a graveyard. Every radio signal we send into space might be the last cry of a civilization that failed to overcome the filter. Humanity today resembles an adolescent. We possess extremely powerful technologies, yet we may not possess the wisdom to use them safely. Statistics are not on our side. If the Great Filter truly lies ahead, then the absence of other civilizations is not mysterious at all. They reached the same stage and did not survive it. If we are truly alone, then the responsibility placed upon us is enormous. Our task is not merely to survive. Our task may be to preserve consciousness in the universe, because if we go extinct, the only light of awareness in this vast cold cosmos might disappear with us. The universe is a dark forest. Every civilization is an armed hunter, silently stalking through the trees, carefully pushing aside branches and trying to move without making a sound. Even breathing must be done cautiously. The hunter has good reason to be afraid. The forest is full of other invisible hunters just like him. If he encounters another life form, another hunter, an angel or a demon, a newborn infant, or an ancient civilization, he has only one option: open fire and eliminate it. In this forest, other civilizations are hell itself. Any life is a deadly threat to all other life and will be destroyed the moment it is discovered. This passage is a quotation from the novel The Dark Forest by Chinese science fiction writer Liu Cixin, the second book of the trilogy Remembrance of Earth's Past. The Dark Forest Hypothesis suggests that every advanced civilization in the universe has a strong incentive to destroy other civilizations as soon as they become technologically detectable. Why? Because it is impossible to know the true intentions of an alien civilization. The enormous distances between stars and the fundamental differences in biology, culture, and psychology make meaningful trust almost impossible. Allowing another civilization to develop freely may be extremely dangerous. Even a weak civilization today might evolve into a powerful rival millions of years later. From a purely strategic perspective, the safest option may be a preemptive strike. Destroy a potential rival before it becomes a real threat. Under this grim hypothesis, the universe may be filled with countless civilizations hiding in silence, carefully avoiding detection. They shut down radio transmissions. They mask technological activity. They avoid any signal that might reveal their presence, all in the desperate hope of not being discovered by another hunter in the dark forest. Which raises a troubling question. Perhaps we should stop broadcasting our presence into space. Some scientists have indeed expressed concern about humanity's attempts to actively send messages to extraterrestrials. Projects such as METI International, Messaging Extraterrestrial Intelligence, have been criticized by figures like Stephen Hawking, who warned that contact with alien civilizations might resemble the encounter between Native Americans and European colonizers. History does not always favor the less technologically advanced. Imagine that you are in Antarctica, observing a colony of penguins. They live their ordinary lives, waddling across the ice and catching fish. Suddenly, one rebellious penguin wanders away from the group and begins climbing far up a mountain. You know it will probably die, but you do not interfere. You do not want to disrupt the natural course of their development. Even a single intervention could alter their entire history. It could disturb the delicate balance of their ecosystem. Evolution must unfold on its own. Now imagine that advanced extraterrestrial civilizations view humanity in the same way. They observe us, but they do not intervene. They do not want to disrupt our natural, technological, and cultural development. They do not want to shock us by revealing their technology. This idea is known as the zoo hypothesis and was proposed in 1973 by astronomer John A. Ball Astric. According to this hypothesis, Earth may function as a kind of cosmic nature reserve, a protected region where extraterrestrial observers watch our development without interference. A more serious version of this idea proposes the existence of a galactic club, a community of advanced civilizations that have agreed not to interfere with emerging civilizations until they reach a certain technological threshold. Of course, a more humorous interpretation also exists. Perhaps they are simply watching us for entertainment. A galaxy-wide reality show. Occasionally they place bets. Which country will start the next war? Or what will happen if another asteroid is nudged in our direction? Perhaps we are looking for extraterrestrial life in the wrong place, or in the wrong way. Humanity has been searching for alien life since ancient times. The first serious experiment in this field was Project Ozma in 1960. A small group of enthusiasts, led by American astronomer Frank Drake, the very author of the Drake equation, used a 25-meter radio telescope at the National Radio Astronomy Observatory, now Green Bank, to search for artificial signals from two nearby sun-like stars, Tau Ceti and Epsilon Eridani. Over 4 months, they detected only one intelligent signal, a transmission from a high-altitude military aircraft. In 1971, the Drake equation became a major reason for establishing the non-profit project SETI, Search for Extraterrestrial Intelligence, which continues to operate today. Search methods include observing exoplanet atmospheres for biosignatures, studying the solar system for microbial life, searching for technosignatures, artificial structures, looking for artificial electromagnetic signals from deep space. It's worth mentioning SETI at Home, launched in 1999, which united thousands of enthusiasts worldwide to provide their computing power for data analysis. The project officially stopped collecting data in 2020, but analysis continues. The main problem in searching for signals is our ignorance. We don't know exactly what to look for, at which frequencies, or where to point our antennas. And what if we did receive a signal, but simply don't understand it? In recent years, the search for alien life has gained new momentum thanks to technological progress. Launched in 2015, Breakthrough Listen is the largest program in history aimed at searching for intelligent extraterrestrial life. Funded by billionaire Yuri Milner, the project received $100 million for 10 years of research. The project uses the Green Bank Radio Telescope, West Virginia, USA, the Parkes Radio Telescope, Australia, the Lick Observatory Optical Telescope, California, USA. Breakthrough Listen scans millions of stars across hundreds of frequencies simultaneously, using advanced machine learning algorithms to analyze the data. Instead of only looking for radio signals, some scientists propose searching for technosignatures, traces of technological activity by civilizations, Dyson spheres, megastructures around stars detectable by anomalies in starlight, atmospheric pollution, industrial gases in exoplanet atmospheres, artificial lighting, night-side illumination of planets with cities, thermal signatures, excess heat from technological activity. Launched in 2021, the James Webb Space Telescope can analyze exoplanet atmospheres with unprecedented precision. It can detect biosignatures, combinations of gases that indicate life, oxygen, methane, ozone. Perhaps we are looking in the wrong place. What if advanced civilizations haven't disappeared or hidden? They have just transitioned to a state beyond our detection methods. Futurist John Smart suggested in 2011 that advanced civilizations do not expand outward into space. As technology develops, everything tends toward miniaturization and higher energy density. Consider human technological history. 1950s computers filled entire rooms. Today, the same computational power fits in a smartphone. Next steps include quantum processors and neural interfaces. Smart proposes that highly developed minds eventually digitize themselves and move into microscopic scales, inward rather than outward. Where do they go? According to the hypothesis, such civilizations create isolated computational environments resembling black holes in terms of information and energy density. Time flows differently inside these spaces. To an outside observer, such civilizations simply vanish from the visible universe. They haven't died. They aren't hiding. They have moved to a level of reality we cannot yet perceive. Why it makes sense? Factor, explanation. Energy efficiency. Computation in small volumes requires less energy. Safety. Isolated environments protect from external threats. Speed. Signals propagate faster in compact spaces. Comfort. Virtual reality can offer more than the physical world. Imagine, instead of colonizing the galaxy, a civilization creates a perfect virtual world inside a single planet. Why travel to the stars if millions of worlds can exist within one server? If technology continues to advance, computational power grows exponentially. What now requires massive data centers could eventually fit within planetary-scale devices. Entire planetary surfaces could theoretically be covered with computing infrastructure, a vast network of processors and storage. Physics also sets immense limits on computation. According to Landauer's principle, every computation has a minimum energy cost. The Bremerman limit defines the maximum computational speed per unit of energy. Even near these fundamental limits, a planet transformed into a computing system could perform astronomical numbers of operations. Physicist Seth Lloyd of Massachusetts Institute of Technology estimated the number of computations 1 kilogram of matter could perform over the age of the universe. An incomprehensibly large number. Roughly 10 circumflex 50 operations. Using the mass of an entire planet, the potential becomes practically unimaginable. Inside such a system, millions, or even billions, of detailed virtual worlds could exist, each the size of a planet, galaxy, or entire universe. To beings inside the simulation, the world would feel completely real. From an efficiency perspective, this may be far more appealing than cosmic expansion. Colonizing the galaxy requires millennia of travel, colossal energy, and constant risk. Virtual worlds can be created almost instantly, in practically unlimited quantity. Thus arises an important implication for the Fermi Paradox. Advanced civilizations may simply lose interest in the outside universe. They do not build vast interstellar empires and leave no detectable traces in space. Instead, they immerse themselves in an infinite number of artificial worlds within their own computational systems. To outsiders, such a civilization may appear nearly invisible. One planet, no galactic expansion, no signals. But inside, millions of universes exist. Not all scientists agree with SMART. The main argument against it, even if a civilization goes inward, it still requires physical resources, energy, materials, cooling. Complete isolation from the universe is impossible. Even virtual civilizations remain physical systems. Computers do not work in a vacuum. They need energy, materials, and cooling. All computations produce heat, Landauer's principle. Heat must be dissipated. Otherwise, the system overheats. Higher computational density makes cooling increasingly difficult. So even hyper-advanced civilizations must interact with the physical environment, building radiators, extracting energy, recycling matter. If civilizations use more and more energy for computation, their activity should be detectable astronomically. For example, they could build massive energy structures around stars, like a hypothetical Dyson sphere proposed by physicist Freeman Dyson. Such megastructures would emit huge amounts of infrared heat because all consumed energy ultimately turns into heat. Astronomers have been searching for these signatures for decades. Both hypotheses offer a comforting perspective on the Fermi Paradox. Transcension, civilizations have not died, they have moved to another level of existence. Dormancy, civilizations are not silent. They are just temporarily inactive. Conclusion: perhaps we are looking for traces of civilizations in the wrong place, at the wrong time. As physicist Michio Kaku said, we may be like ants trying to understand the internet. Our technology has not yet reached the level to see what already exists. Or perhaps we are among the first to ask the question aloud. One day, millions of years from now, another civilization may study our signals and ask, where was everyone? Another possibility: we might be among the first intelligent civilizations in the universe. Research in 2016 suggests that 92% of all stars that will ever exist have not yet been born. Most stars will form in the distant future, especially around red dwarfs that live for trillions of years. Perhaps life requires a certain level of stellar metallicity, the presence of heavy elements, which has only recently been achieved in the universe's history. By this hypothesis, humanity has not arrived too late. We came early. We may be among the first civilizations to reach a technological level. The Fermi Paradox remains one of science's deepest mysteries. We have many hypotheses, but none are confirmed. What can we do? 1. Keep searching. Projects like SETI and Breakthrough listen expand our reach. 2. Study our planet. Searching for life in extreme Earth environments helps us understand where else it may exist. 3. Explore the solar system. Mars, Europa, and Enceladus may hide microbial life. 4. Develop technology. Better telescopes, more sensitive detectors, AI for data analysis. 5. Be cautious. If the dark forest hypothesis is true, broadcasting signals may be dangerous. Why it matters, the answer to where is everyone, will reshape our understanding of humanity's place in the universe. Finding another civilization would be the greatest discovery in history. Confirming that we are alone would place immense responsibility on us. As Carl Sagan said, somewhere, something incredible is waiting to be known. We must find that page in the book of the universe. Meanwhile, we listen, search, wait, and in the silence of space, continue asking the question Enrico Fermi posed over 70 years ago. Where is everyone?